So Cartesian geometry, fancy name for coordinate geometry, of course. The distance formula would have been one of the first formulas we saw, which really is just Pythagoras' theorem when you think about it. So there it is, distance is the square root of the difference in the x values squared. So that would be one side of the triangle. Difference in the y values squared, there's the other side of the triangle, and obviously the distance between the 2 points is the length of the hypotenuse. Quick little example, -1, 3, 3, 5. Look, a lot of people get paranoid with this, and you don't need to. In that they say, oh, hang on, if I started with x2 here, so I started with which one did I start with? I didn't even start with the x's, I started with the y's, there you go. If I started with the x2 here, then I've got to have the y2 and things like that. It doesn't matter in this because you're squaring it anyway. So if you got them the other way round, well, when you square it, the negative will become positive. So it really doesn't matter, as long as it is just the difference in the x values plus the difference in the y values squared. And as I say, I actually ended up doing the y values first on mine. So, hey, who cares? You know, that gets the answer. And ends up with 2 root 5, of course. So as I say, that really is just finding the length of a hypotenuse in a right angle triangle. That's all it really is. The other one we see a lot of is midpoint. This one, again, it doesn't matter because the order of addition, you know, a plus b is the same as b plus a. Okay, make sure it is the x's and the y's are right. But so let's do this one. Add them together, divide by 2. But midpoint, if you look at the name of it, it's exactly what it is. You're finding the average. So of course you add them together and divide by 2. So you're just saying, oh, what's the average of the x values? What's the average of the y values? Okay. The other thing is using Euclidean geometry to solve coordinate geometry problems. Right? It's all geometry. It doesn't really matter, one's Euclidean, one's Cartesian. You sometimes get those problems. So the ideas you may recall from Euclidean geometry, angle sum of a triangle, all those sorts of things. If you want to show something's a parallelogram, opposite sides are parallel, all those sorts of things. You still use them in the Cartesian geometry. Classifying quadrilateral is probably worth pointing out because I guess in Cartesian geometry you don't get a lot of questions which says what's the size of the angle or something like that. You don't get a lot of those. You get more like what type of quadrilateral is this? You know, so things like that. So the features they possess, that's how we classify them. Right? So there's our little family tree for quadrilaterals, and as you branch down the tree it gets more and more specialised, if you like, more features start coming out. But any feature of something that it comes from can still be used in the one below. So the example I've got there is a rhombus. Now a rhombus is a parallelogram, so you could use any property of a parallelogram in a rhombus. It is a kite, so you could use, for instance, you could use the formula for the area of a kite to find the area of a rhombus, and in fact you do. I don't know if you realise that or not, but the formula that people often quote for the area of a rhombus is actually the formula for the area of a kite, which of course is half the product of the diagonals. Okay, so let's go into a bit more detail. Shapes of quadrilateral, that doesn't tell us a heck of a lot. Oh, it's got 4 sides. And it's got 4 angles, fantastic. But other than that, I mean, doesn't really tell us much. So the quadrilateral, as I say, branches down, could be a kite. So what makes it a kite? And that's where you've got your pair of adjacent sides are equal. Diagonals in a kite will always be perpendicular. So that's another feature of a kite. And as I say, the area of a kite, half xy, where xy are the diagonals. So if you had to prove something was a kite, if you could show the diagonals were perpendicular to each other, that would be good enough. Right? Of course, it could branch off and be a trapezium. And in a trapezium, we know one of the pair of sides is parallel. And the formula we have for that one is half the perpendicular height, sum of those parallel sides. Branch down to a parallelogram. So a parallelogram is a trapezium that's just got a little bit more specialised. Now we know that both pairs of sides are parallel. Opposite sides in a parallelogram, we also know they're going to be equal. So that's another way we could show shapes of parallelogram. Opposite angles in a parallelogram are equal. Probably don't use that one that much in coordinate geometry, because that would require us to find the angle between things, and probably don't. Diagonals in a parallelogram bisect each other. That's another one. The area of a parallelogram, of course, is base times perpendicular height. There is another way for showing parallelograms. It's where we get sort of two of these and show half of it. Huh? So what I mean is, if you're just playing with one pair of sides, but you can show they're both parallel and equal, so it's sort of like combining the first two together, then that's enough to say it's a parallelogram. You don't have to do the other pair of sides as well. Okay? So kite and parallelogram. Well, parallelogram can get a bit more specialised again, becomes a rectangle. So what's happened? Now we know the angle inside the rectangle has become 90 degrees. And now the diagonals become equal. So if you've now got equal diagonals, and you know it's a parallelogram, then that must be a rectangle. And we get to base times length, of course. Rhombus, which is both a parallelogram and a kite. So it's all the features of both parallelogram and kite, but it also has this one that will end up bisecting the vertex. Again, in coordinate geometry, we probably don't use it that much because that deals with knowing the size of the angles. And then we have the perfect quadrilateral, the square, which really doesn't have any features on its own. It's just that it has every feature of every quadrilateral. It's the perfect quadrilateral. And if you really wanted a formula for area, I suppose you could. Amazingly, is the square is s squared. There's a formula. All right, let's have a look at some examples. So we've got 4 points, and they want us to show that this particular shape is indeed a rhombus. So we've got different ways available to us. I'm going to find the midpoint of AC. So it's just averaging the x and the y values. I'll find the midpoint of BD, and what do you know? They're equal. So I know the diagonals bisect each other. So I know it's a parallelogram. So I don't know it's a rhombus at this stage. That was a condition for a parallelogram. So I've proven the diagonals bisect. Now, to prove it is indeed a rhombus, I'll have a look at the lengths. And if I can show that the adjacent sides are equal, that'll make it a kite. But if it's both a kite and a parallelogram, then it must be a rhombus. So the length of CD is 5. The length of AD is also 5. So, yep. So I know it's a rhombus. And just like with Euclidean geometry, it's no different in Cartesian geometry. If you're proving something, you write down reasoning. You say, well, okay, this is how I know this to be true. So I know I've got a parallelogram with adjacent sides that are equal. It's got to be a rhombus. There we go. So that's just one example. There are other ways, of course, of proving that. That was just one. So 7A in our books. And that's it. Time to start work. Woohoo, we're back.